Okay, and we're back here concluding this problem. So if we look at this left-hand side and combine like terms, we find negative 4a sine of 2t plus a sine of 2t gives me negative 3a sine of 2t. And we have minus 4b cosine of 2t plus b cosine of 2t is minus 3b cosine of 2t. And that should equal 1 sine of 2t plus 0 cosine of 2t. And if this is in fact equal, then the coefficients on the left and the right-hand side of the corresponding terms have to be the same. So that forces a to have to be negative 1/3 and b have to be 0. Therefore, the particular solution is going to be, stick a negative 1/3 up here and a 0 for b, negative 1/3 sine of 2t, combined with our complementary solution, we get the overall solution. So this has got to be x. So x of t is equal to c1 cosine of t plus c2 sine of t minus 1/3 sine of 2t. Okay. All right, so we've now solved this guy. We solved our differential equation, and we can find c1 and c2 using our initial values. So 0 is x of 0, and so that's going to be, if I stick a 0 in for t, we get 0 on the left-hand side. Cosine of 0 is 1, so I'll just get c1 plus sine of 0 is 0 and sine of 2 times 0 is 0. Oh, so that's nice. So that tells me that c1 equals 0. We also know that x prime 0 is 0, but this guy's going to require a little bit more work. So let's do the derivative here. X prime of t is going to be, well, if we know that c1 is 0, let me just note that here. So this guy's 0, so that term isn't going to happen. So great news is we can take this guy and do his derivative. The derivative of c2 times sine of t will be c2 times cosine of t. And the derivative of this guy will be minus 2/3 cosine of 2t. And if we stick a 0 in for that guy, for t, we're going to get c2 minus 2/3. So 0 equals c2 minus 2/3. And if we add 2/3 to both sides, so let me just write this again, 0 equals c2 minus 2/3. So c2 equals 2/3. And remembering that c1 was 0, we now have, finally, using techniques that we've done before without Laplace transforms, our final solution to our initial value problem. And that will be x of t equals, remember that c1 was 0, c2 is 2/3. So we'll have 2/3 sine of t minus 1/3 sine of 2t. Okay. And we have now completed the solution to our initial value problem. Now, let's go back and remember what we learned last section. So with last section, we learned that with Laplace transforms, okay, what we just did was all of this guy. So we did the hard work involving a lot of derivatives. Okay, and we then found our solution to our non-homogeneous solution. Now, we're going to tell you about the Laplace method here in just a second, but I need to introduce just a little bit more theory for the Laplace method to work. So remember that if we take a function, we can do his Laplace transform and get the Laplace transform of the function, which we call capital F of s. So what would happen if I do the derivative of, not the function, but the derivative of his, or sorry, the Laplace transform of his derivative? Well, as it turns out, it's going to be s times the Laplace transform of f of t minus f of 0. Or in other words, s times f of s minus f of 0. Okay. Doing it again, the second derivative is going to give us s squared times cap f of s minus s times f of 0 minus f prime of 0. And we can continue to a third derivative and higher derivatives as necessary. Okay. So let's redo our problem that we did just a minute ago. Same exact differential equation, same exact initial values, but we're going to use the Laplace method. So we're going to name our solution x of t, little x of t. So his Laplace transform will be capital X of s. The Laplace transform on x prime of t. So we're going to be doing the exact same thing we did here, but instead of calling the function f, we're calling it x. So that's going to be s times cap x of s minus x of 0. So that's going to be s capital X of s minus x of 0 we know to be 0. So that is simply s times x of s. Okay. And the second, Laplace derivative on the second, Laplace transform on the second derivative is s squared times capital X of s minus s times x of 0 minus x prime of 0. And we notice that these two terms are both 0. So it's simply going to give us s squared cap x of s. And finally, we need to handle the non-homogeneous piece, the Laplace transform of sine of 2t, which we've seen at the end of last time and in our table. That's going to be 2 over s squared plus 4. So if we substitute all this into our original differential equation, so if we do the Laplace transform on the whole differential equation here, we're going to get the Laplace transform of x double prime, which is s squared times cap x of s, plus the Laplace transform on x equals sine of 2t and his Laplace transform. Here's what the transform differential equation will look like. Now, the great news is there are no derivatives here. So the Laplace transform method way is good because you don't have to do any derivatives. You need to focus primarily on algebra. So what we're going to do is solve this for capital X of s. And if we do that, so if we factor out the x of s on the left-hand side, we're left with s squared plus 1. And then dividing both sides by s squared plus 1, we get capital X of s is 2 over the quantity s squared plus 4 times s squared plus 1, which we saw on the very first page that this is equal to negative 2/3 plus 2/3 right here. Okay. Or if I wanted to, I could write this as negative 1/3 times 2 over s squared plus 4 plus 2/3 times 1 over s squared plus 1. And that's this guy. So now to get back to the original solution, we have to do the inverse Laplace transform. Ooh, let me slide that up. And doing the inverse Laplace transform, okay, you'll notice that this guy, I factored out the negative 1/3, leaving the 2 on top, so that this guy looks like the s squared plus 2 squared, which we know from our table, this guy, so let me just do one more step here. The inverse Laplace transform of, and we'll factor out the negative 1/3 inverse Laplace transform of 2 over s squared plus 2 squared plus 2/3 times the inverse Laplace transform of 1 over s squared plus 1, which, doing the inverse Laplace transforms or reading our table the other direction, we will get that x of t is equal to negative 1/3 times, this was sine of 2t plus 2/3 times, this inverse Laplace transform is sine of t. And you should note that that is identical to what we had doing it the other way around. Cool. So I'll let you think about this. Which method was more efficient, the undetermined coefficients or the Laplace transform way?